Hey everyone, so today we are going to be talking about rational functions and their graphs. So, let's get started. So, if we're going to talk about rational functions and their graphs, then it makes sense that the first thing we talk about is what is a rational function? The definition of a rational function is as follows. Rational functions are quotients of polynomial functions. Okay, cool. But what does that mean? What this means is that rational functions are functions that can be expressed as this. F of x is equal to p of x over q of x, where p and q are polynomial functions and q of x is not equal to 0. Now, why can't we have q of x equal to 0? Because if it was equal to 0, then at some point we're going to have something that's not 0 divided by something that is 0. And as we all know, you can't divide by 0, so we need to have this condition in here to prevent us from dividing by 0. Now that we've defined it, let's talk about the domain of it. The domain of rational functions are the set of all real numbers except the x values that make the denominator 0. So, the reason we have to have this is because if we have any values in the domain that make the denominator 0, then we're basically saying we can divide by 0, which makes absolutely no sense. So we have to get rid of those values from the domain. Now that we've defined it and talked about it, the domain, about what it is for a second, let's come up with a couple examples of rational functions. First up to bat, we have f of x is equal to x squared plus 4 over phi of x. The numerator is the degree 2 polynomial x squared plus 4, and the denominator is the degree 1 polynomial 5x. Now, g of x. G of x is equal to 42x over 15x squared plus 2. So in the numerator, we have a polynomial of 42x, and in the denominator, we have a polynomial of 15x squared plus 2. So these are two basic examples of rational functions. Now that we've seen a couple of them, let's see if we can go find the domain of these rational functions. So consider the rational function f of x is equal to x squared minus 4 over x minus 2. Recall that the domain consists only of the values of real numbers that do not make the denominator 0. So in order to find the domain, we need to go find the values of x that make the denominator equal to 0 and kick those out. We don't want those. No good. So set the denominator equal to 0. X minus 2 is equal to 0. Add 2 to both sides, and we come up with x is equal to 2. What this means is the value x is equal to 2 makes the denominator 0, hence we cannot have 2 in our domain. So we say that the domain consists of all real numbers except 2. Now, there are two main ways to write down the domain. We can express the domain in set builder notation or in interval notation. So let's take a look at both of those. First up, set builder notation. For set builder notation, we say that the domain of f is equal to the set of all x and r such that x is not equal to 2. Straightforward, concise, but we have another way of expressing the domain with interval notation. And we say that the domain of f is equal to the open set negative infinity to 2 union the open set 2 to infinity. Now pay close attention here. We have parentheses around the 2's because we are talking about open sets. Now, if we had a bracket there, that would mean it's everything in that interval including 2. But we need to write the domain down without 2. 2's not in the domain. So if we have a way of writing down the domain that includes 2 in this context, then we done gone goofed up. So We can't have that. That's why there's no brackets there. That's why everything involved is a parenthesis. Now, we had a bracket around infinity. That makes even less sense because that means we're including infinity in the domain, but domain has to be real numbers. And we include it in there. That just means we have just said infinity is a real number, and that makes about as much sense as dividing by 0. So that's why we have parentheses all around. It's a parentheses party. So that's one example. Now let's consider the second example. Find the domain of the rational function g of x is equal to x over x squared minus 25. So we have been tasked with figuring out what the domain of this function is. Now, before I go over my solution, I'm going to pause here for a couple seconds so you can pause this video and give this a try yourself. So go ahead, pause the video and see if you can figure out what the domain of this function is. All right? Hopefully you attempted at finding the domain of this rational function, and if you did, let's go over the solution. And if you didn't, well, let's go over the solution anyways. So, solution. We want to find the x values that make the denominator equal to 0. So, set the denominator equal to 0. And when we do that, we get x squared minus 25 is equal to 0. Add 25 to both sides, and we come up with x squared is equal to 25. So now we take the square root of both sides, and we conclude that x must be equal to 5, or x must be equal to negative 5. Now, since we took the square root, you can't forget about that pesky negative 5. When we take the square root, you need both the positive root and the negative root. They're both candidates for this, okay? So from that, we conclude that the domain consists of all real numbers except plus or minus 5. Now, just like that last example we just did, we can express this in two different ways, in set builder notation and interval notation. First up, set builder notation. So the domain of G is equal to the set of x such that x is not equal to 5 or x is not equal to negative 5. So that's how we would write this domain down in set builder notation. Next up, interval notation. The domain of G is equal to the set negative infinity to negative 5, union negative 5, comma 5, union 5, comma infinity. Once again, notice the usage of parentheses and not brackets. If we have brackets anywhere in here, then we messed up somewhere. If we have brackets in here, then we're saying that these values are included in the domain. But as from the analysis we did on the previous slide, that can't happen. So that's why we're using parentheses here. Both of these are equally valid ways of writing the domain, but if you're asked on an exam or homework to write down the domain of a function, check to see which way it specifies, set builder notation or interval notation. Okay? Now, let's move on to asymptotes. Fun stuff. So, we've talked about the domain of rational functions, the definition of rational functions, and now let's talk about these vertical asymptotes. Okay? What is a vertical asymptote? The line x is equal to a is a vertical asymptote of f if f of x goes towards plus or minus infinity as f approaches a. Okay? What does that mean? So, let's draw a Cartesian graph here. Let's plot a vertical asymptote right here. Okay, cool. Now, what they're saying is we're getting closer and closer to this vertical asymptote as these x values get closer to a. The function values themselves are going to take off towards plus infinity or minus infinity. And in this example, they take off towards plus infinity. Now notice this. It goes up really close next to it, but it never actually breaks that barrier. And so as we get closer and closer, it's going to take off to infinity, and it's going to hug that line, but it's never actually going to cross that line. That's one of the cool things about these vertical asymptotes. They're walls that exist on the plane where the function will run up into it, but it can never cross it. So, we just talked about the definition of a vertical asymptote, and that's all fine and dandy, but it doesn't really matter much to have this definition in hand if we don't know how to go and find these vertical asymptotes. So that's what we're going to talk about right now, locating vertical asymptotes. So since we've been talking about rational functions, let's just pick an arbitrary rational function f of x equal to p of x over q of x, such that p and x and q of x have no common factors with each other. So, if a is a real number, notice that part, real number, such that q of a is equal to 0 and p of a is not equal to 0, then the vertical line x is equal to a is a vertical asymptote of the graph of f. Man, that's a mouthful. But let's break this down. So, have a real number in our hand, a, that makes the polynomial in the denominator, q, equal to 0 at that point. But it doesn't make our numerator polynomial p of a equal to 0. Then we can draw a vertical line at a such that it becomes a vertical asymptote for the graph of f. Now, let's see an example of how to find these vertical asymptotes now that we have this technique in hand. So, let's consider this function. F of x is equal to x over x squared minus 1. Now, solution. The numerator and denominator do not have any common factors, so we have the proper setup we need to use that technique we just discussed. So, we need to find the x values that make that denominator polynomial x squared minus 1 equal to 0. To do that, set x squared minus 1 equal to 0, add 1 to both sides, and then take the square root, and so we can conclude that x must equal negative 1 or x must equal to 1. So what that means is if x is equal to negative 1 or x is equal to 1, then the denominator is equal to 0 and the numerator is not equal to 0. So we have two vertical asymptotes, one at negative 1 and one at 1. So let's put those up on the board. We have x is equal to negative 1 and we have x is equal to 1. Now, we're talking about finding vertical asymptotes of functions, so it makes sense to graph these things. In a graph, we need our Cartesian plane. Now, let's put our vertical asymptotes on this thing. So, we have a vertical asymptote at negative 1, and we have a vertical asymptote at x is equal to 1. Now, let's see how this function behaves as we graph it and it approaches these vertical asymptotes. As we come in from the right, the function values get close to that x is equal to 1 barrier and take off to 1, but it never crosses it. Now, if we go into that middle segment, and if we can see that that function approaches both vertical asymptotes, negative 1 and 1, takes off to plus infinity and minus infinity respectively, however, never actually touches it. And then on the left side, we have the function approaches that vertical asymptote at negative 1, and then takes off down towards negative infinity, but never actually touches the vertical line. So the vertical asymptotes behave sort of like a wall in an ocean, and the function is a wave, and it comes crashing up against it, but it never actually penetrates it. It never goes through it. It gets really close up to it, smack into it, but it never actually touches it, never actually enters it. So that's what these vertical asymptotes are. This is what it looks like graphically. This is a decent example for it. And it provides a little bit of more intuition as to how these behave with respect to their graphs. Now, let's consider another function. F of x is equal to x over x squared plus 1. Now, they have no common factors, so we need to find the x values that make the denominator vanish. So, to do that, set x squared plus 1 is equal to 0. Subtract 1 from both sides. We have x squared is equal to negative 1. And now we're going to take the square root of both sides, and then we can conclude definitively that we have vertical asymptotes at plus or minus I. Wait a second. That's a problem. If you look back at that definition for vertical asymptotes exist at real numbers. I is by no means a real number. So, since the only values that make this denominator equal to 0 are imaginary numbers, well, from that, we can conclude that we do not have any vertical asymptotes for this function. Fun stuff. All right. Now we spent a lot of time talking about vertical asymptotes. it only makes sense to now ask the question, well, what about horizontal asymptotes? Do we have similar behavior, but horizontally rather than vertically? That answer is yes. So let's define these vertical asymptotes. The line y is equal to b is a horizontal asymptote of the graph of a function f if f of x approaches b as x tends towards plus or minus infinity. Okay, so again, that's a mouthful. Let's look at what this means. So let's suppose we have this horizontal asymptote, this horizontal line at y is equal to b, right here. Now what this means is we were to draw some function f, and as we go towards positive infinity, as those x values get bigger and bigger and bigger in magnitude, our function values are going to start hugging this horizontal line right here, this horizontal asymptote. Now, the difference between a horizontal and vertical asymptote, besides the fact that one's horizontal and one's vertical, is that you can actually cross a horizontal asymptote. A horizontal asymptote doesn't behave like this rigid structure like the vertical asymptote, this tough, strong wall. It's more of a trend line. It's saying that as our x values get bigger and bigger and bigger here, the function values will start to converge or tend to this y is equal to b value. So that's kind of an important distinction between a vertical and horizontal asymptote, and it's very important to keep that in mind when we're talking about asymptotes. So once again, we've introduced a new definition, so it only makes sense now to look at an example in finding these horizontal asymptotes. So picking a rational function f, then it can be written as this. Now, don't panic when you see that. I know that looks a little scary, but let's just break this down and look at this. F of x is equal to a polynomial of degree n with coefficients a. This a sub n minus 1, a1, and a0. These a values are just real numbers. They're the coefficients of this polynomial. In the denominator, we have a polynomial of degree m with these b values for coefficients. This bm, this b1, this b0. These are just coefficients of this polynomial in the denominator. So this is another way to view rational functions. This is the exact same way we defined it. However, we just have a more explicit form for our p of x and our q of x. So don't get scared by that. So from this, we can conclude that the degree of the numerator is n, the degree of the denominator is m. Now, these are the only two pieces of information that we're really going to need in determining horizontal asymptotes. So, we got a rational function in this form. Then there are three cases for horizontal asymptotes. Case number one is if the degree of the numerator is less than the degree of the denominator. In that case, the horizontal asymptote is the line y is equal to 0, or the x-axis. Now, case number two, if the degree of the numerator is equal to the degree of the denominator. Wow, my voice just cracked right there. Excuse me for that. So, if n degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is simply the ratio of the two leading coefficients, or the coefficients that are in front of the highest power term. So in this case, that an over bm. So if the degrees are equal, we take those two leading coefficients, and their ratio is where our horizontal asymptote is. Now, case number one is if n is less than m. Case number two is n is equal to m. I think we take a guess at what case number three is, and lo and behold, if n is greater than m, it's case number three. Now, the degree of the numerator is greater than the degree of the denominator, then f actually has no horizontal asymptote. And that means we call it a day on that one. The degree of the numerator is bigger than the degree of the denominator. We don't have a horizontal asymptote, and we can move on with our lives. Okay? So these are our three cases for evaluating and finding horizontal asymptotes. Now, let's look at an example. Consider the function f of x, 9x squared over 3x squared plus 1. And we've been tasked with finding the horizontal asymptotes of this function. Okay? First thing we need to do check out the degrees of the numerator and the denominator. The degree of the numerator is equal to 2. The degree of the denominator is also equal to 2. So this is case number 2, where n is equal to m. So we can conclude that the horizontal asymptote is the line y is equal to a sub 2 over b sub 2. Or in this case, 9 over 3, which is simply y is equal to 3. Recap, since the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is simply the line equal to the ratio of the leading coefficients, so 9 over 3, which is just simply y is equal to 3. Now, consider another function. Find the horizontal asymptote of g of x is equal to 9x over 3x squared plus 1. Now, take a second and see if you can figure out the horizontal asymptotes. Pause the video here and go give it a try. Okay? So, if you went and found your horizontal asymptote, if you think you have it, let's look at this solution and see if you were right. If you didn't give it an attempt, well, let's still look at it anyways. So, solution. We know the degree of the numerator is equal to 1 this time. It's not equal to 2 like last time. Now it's equal to 1. The degree of the denominator is equal to 2. So this is a case 1 situation where the degree of the numerator is greater than the degree of the denominator. So we can come to the conclusion that the x-axis is the horizontal asymptote for this function, or the line y is equal to 0. Now, we spent a lot of time talking about vertical and horizontal asymptotes. Now let's move on to another property of functions, specifically for rational functions, symmetry. First up to bat, odd symmetry. So, what do we mean by odd symmetry? Suppose we have a function that looks something like this. Now that looks pretty well behaved. It looks symmetric. In fact, if we draw this dashed line through the origin, we can see that the function is symmetric about this line. Now analytically, what that means is that f of negative x is equal to negative f of x for all x in the domain. So we can kind of pull that negative value out from the input. This is the defining characteristic for an odd function. Okay. This means it has origin symmetry. It means it is symmetric about the origin. So take the function and we spin it however we want around this line, we're going to end up exactly where we started. Now, since we've talked about odd symmetry, it only makes sense now to talk about even symmetry. Now, what do I mean by even symmetry? A function is even if it has this property. F of negative x is equal to f of x. Now, odd functions, we were symmetric about the origin. With even functions, however, we are symmetric around that y-axis. Which means is if we have a function that looks something like this, and if we flip it around the y-axis, and we end up back where we started, then it has even symmetry. Cool. Now, let's talk about graphing rational functions. The first way we're going to do this is by using transformations. And when we're using transformations to graph a rational function, we want to start with a parent function, a simple function that we know how to work with. And what we're going to choose is the function f of x is equal to 1 over x. We are going to use this, along with transformations, to graph the function g of x equal to 1 over x plus 2 minus 1. So, we want to use this function 1 over x, transform it, and get the graph for g of x. So, let's go about how to do that. So, first up, we begin with f of x is equal to 1 over x, which makes sense given that we want to graph g of x based on this function. So, let's start with this function 1 over x. We have our Cartesian plane, and let's graph it. So, this is our starting point. This is the function we are going to start graphing with. So, first up, we need to shift 2 units to the left in order to get f of x to look like this, 1 over x plus 2. Now I know you're looking at that plus 2 and you want to shift it to the right, but since this is a transformation on the input, we need to shift it 2 units to the left, not to the right. Now, let's actually shift this. Boom. 2 units to the left. Cool. Now, this isn't quite like g of x. We're not done yet. We still have one more step we need to go. We need to shift this 1 unit down and get f of x is equal to 1 over x plus 2 minus 1. So we shift it down 1, and there we go. Now this is our graph of g of x. So we used a parent function 1 over x, transformed it a little bit, shifted the graph a couple of times, and we ended up with another rational function. So this is a technique for graphing rational functions using transformations. Now, you might not always be in a situation where you want to use transformations to graph a rational function. So now we're going to discuss a strategy for graphing an arbitrary rational function using all of these techniques and all of these ideas we've been building up for the last 20-25 minutes. So first up, start with the rational function that we want to graph, with p of x being the polynomial in the numerator, q of x being the polynomial in the denominator. Step 1, determine where the function has symmetry. As you recall, what we mean by symmetry is it symmetric about the y-axis, or is it even, or is it odd? And is it symmetric about the origin? So that's our first step, determine its symmetry. Step 2, find the y-intercept. Now, the y-intercept is where the function intersects the y-axis, or where x is equal to 0. So to find it, we need to evaluate f of 0. And whatever that value is, that's our y-intercept. Now, if we're going to talk about the y-intercept, we kind of need to talk about the x-intercepts. If you're going to talk about the y-intercept but not the x-intercept, then the x-intercept is just going to throw a fit. It's going to feel like you're leaving it out. So if you're going to check one intercept, you got to check the other intercepts. To check for the x-intercepts, what we need to do is solve the equation p of x is equal to 0, where p of x is our numerator polynomial. So the x-intercepts are the values of x that make the numerator equal to 0. Now, let's move on to asymptotes. We need to find the vertical asymptotes first. So what we need to do is we need to set the denominator of q of x equal to 0, and then the values that make that equal to 0 are our vertical asymptotes. But just like the situation with the intercepts, what you do to one side, you got to do the other side. So if you find vertical asymptotes, you got to find the horizontal asymptotes. You can't just find one and call it a day. You got to find both. Otherwise, they're just going to get cranky. So, to find the horizontal asymptotes, we compare the degrees of the numerator polynomial and the denominator polynomial, and then use our 3 cases to figure out what our horizontal asymptotes are. Step 6. The previous 5 steps give us a lot of useful information, but they don't give us all the information. So what we need to do is plot at least one point between and beyond each x-intercept and each vertical asymptote. So all that information from those previous 5 steps gives a lot of useful and powerful information, but it's not quite enough for what we need in order to start graphing stuff. So this step 6 provides us with a little extra information to give us that little extra push to get a well-drawn graph. Now, step 7 is the most obvious one. Use the above information to actually, graph the thing. So it'd be kind of a shame if we went through all those steps and we ended up not graphing it. So don't forget step 7. Actually graph it. Okay? So now that we've gone over the strategy, it makes sense to use this strategy to actually graph an actual example. So let's consider this function. F of x is equal to 3x minus 3 over x minus 2. Let's graph this. Let's use the strategy that we've gone over and graph the thing. Step 1, determine the symmetry, if it has any. So, to do that, plug in negative x into your function and see what your output is. So, go about the process of subbing in x for negative x, do some algebraic manipulation, and we end up with this. Now, notice, this isn't equal to f of x, nor is it equal to negative f of x. So from that, f of negative x is not equal to negative f of x, and f of negative x is not equal to f of x. So we can conclude that f has no y-axis symmetry, nor does it have origin symmetry. Now you might be thinking, great, we just wasted our time figuring that out. The fact that we've just shown that there is no y-axis symmetry, no origin symmetry, actually tells us information about this graph. For example, if you start graphing it, and you have one of these two kinds of symmetry, then a mistake has probably been made somewhere else in the process, and you probably need to go back and recheck your work. So while we don't have symmetry, this is still useful information for us. Step 2, find the y-intercept. To do that, evaluate f of 0. So take our function f, replace x with 0, evaluate it, and we conclude that the y-intercept is equal to 3/2. Now, since we found the y-intercept, now we have to go find the x-intercepts, otherwise they're just going to get jealous. So we need to solve the 3x minus 3 is equal to 0, because 3x minus 3 is our polynomial in our numerator. So we set it equal to 0, move that 3 over, divide both sides by 3, and so we find that our x-intercept is simply x equal to 1. It's all good information. So, now, let's move on to step 4. Find the vertical asymptotes. And we recall from earlier in this video, to find the vertical asymptotes, what we need to do is set the denominator equal to 0 and solve. So that's what we're going to do. Set x minus 2 is equal to 0, move the 2 over, and we get x is equal to 2 as our vertical asymptote. Now, just like with the intercepts, if we found the vertical asymptote, we need to find the horizontal asymptote. Just by inspection, we can see that the degree of the numerator is equal to 1, the degree of the denominator is equal to 1, so that means the degree of the denominator equals the degree of the numerator. And you refer back to your cases, that means your horizontal asymptote is simply the ratio of the leading coefficients. And the leading coefficients are 3 and 1, so our horizontal asymptote is equal to 3 over 1, which is equal to 3. Now, we're going to move on to graphing this thing. We're going to combine 6 and 7 here into one kind of motion here. And let's kind of bring together all the information we've got from the previous steps. So we have our x-intercept at the point 0, 1, our y-intercept at 0, 3 over 2, vertical asymptote at x equal to 2, horizontal asymptote at y is equal to 3, and now let's plot everything. Got our x-intercept there, our y-intercept here, vertical asymptote here, and horizontal asymptote here. Now, from step 6, we can plot a few points between our intercepts and our vertical asymptotes, and then we can actually draw our graph, and we end up with something like this. I know it's a lot of steps, but they're all simple steps and straightforward, and it can result in a good looking graph. Now let's move on to application. Let's consider the problem. A company is planning to manufacture wheelchairs that are light, fast, and beautiful. Okay, apparently you can have beautiful wheelchairs. I didn't know that, but apparently you can. The fixed monthly cost will be $500,000, and it will cost $400 to produce each radically innovative chair. So, let's write down the cost function C of producing X amount of wheelchairs. Solution: C of X is equal to $500,000, because that's our fixed monthly cost, plus $400 per each wheelchair. So we can conclude that our cost function is equal to 500,000 plus 400x. Okay? Consider the same problem. Now, what about the average cost function of producing X wheelchairs? Well, that is just simply our cost function divided by the number of wheelchairs that we produced. The average cost function gives us the average cost per wheelchair. So now, let's do some stuff with that. Find and interpret C bar of 10,000, or the average cost of 10,000 wheelchairs. See, bar of x is equal to 500,000 plus 400x over x. Plug in 10,000, and we get that the average cost is equal to $450. Now what that means is the average cost per wheelchair after we've produced 10,000 wheelchairs per month is $450. Now, find the horizontal asymptote for the average cost function. See if x is equal to 500,000 plus 400x over x. Solution? So, we have our function. We recognize that the degree of the numerator is equal to the degree of the denominator. So, the horizontal asymptote is simply the ratio of the leading coefficients, or y is equal to 400. Now, that's all fine and dandy, but what does that mean? What in the context does this horizontal asymptote tell us? Well, what it tells us is that as we start producing more and more wheelchairs, as we start producing a lot of them per month, the average cost per wheelchair is going to approach $400 each as we keep producing wheelchairs. So as we start producing 10,000, 20,000, 40,000, 50,000 wheelchairs per month, the average cost per wheelchair is going to approach $400 each. Now, that's all I have for you today. I hope you enjoyed this and learned something about rational functions and their graphs.